Alright, welcome back. Now in the last video we talked about amplitude phase form of the general solution, where instead of having two sinusoids, we have a one sinusoidal term with the undetermined coefficients corresponding to an amplitude and a phase. Now I just want to emphasize that no form is strictly better than the other form. They each have their own merits. One form may be particularly useful on one type of problem, another form on another. This form may be easier to graph for you, but this form may be easier to find initial conditions for. They both are really handy at times. So what we're going to do in this video is we're going to mathematically show how we can rederive this formula from this expression here. And in doing so, we're going to actually need to use a couple of trig identities. In particular, the adding angles identities. So let's just write those out here right now. So what we're going to use is cosine of A plus B is equal to, let's see if I get this right, cosine A times cosine of B minus sine of A times sine of B. And just for completeness, I'm just going to put the other adding angles formula, which is sine of A plus B is equal to sine of A times cosine of B plus sine of B times cosine of A. Now, these are two really important formulas, really handy to know. There are very nice, elegant proofs for them, but we're not going to go over them here. Right now, we're going to apply this formula here for our amplitude phase form. So we're going to say that C cosine omega t minus phi, and we're going to apply this equation. So we're going to say that omega t corresponds to our A. And we're going to say that negative phi corresponds to our B. So if we do it out, we're going to get C times, let's just say parentheses, cosine of A, which means cosine omega t, times cosine of B, which is cosine negative phi, minus sine of A, which corresponds to sine of omega t, times sine of B, which corresponds to sine of negative phi. So let's try and simplify this up a bit. Let's in particular look at these cosine negative phi and sine negative phi terms. In order to simplify them, we're going to have to invoke one other trigonometric rule or identity. You may or may not remember that cosine is what we like to call an even function. What this means is that cosine of negative phi is equal to cosine of phi. Now sine, on the other hand, is what we like to call an odd function. Whoops. There we go. Odd function. Now what this means is that sine of negative phi is equal to the negative sine of phi. Now this is actually fairly handy and fairly quick to prove, so we're just going to do it out right now. Let's actually go back to our unit circle in order to show where we got this. So here's our circle. Here's our y-axis, and here's our x-axis. And since it's a unit circle, the radius of this circle is 1. Now let's just say that we have an arbitrary angle from the x-axis phi. This angle will correspond to one point on the unit circle, and let's just call that x, and it'll correspond to this y point. Let's say that corresponds to xy. Now what happens if we look at the negative phi, going down in the opposite direction? So this angle here is negative phi. What point does this correspond to? Well, it corresponds actually to the same x point, and it actually will correspond to the negative y point. So you may be saying, well, that's pretty neat, but what does it have to do with our sine and cosine? Well, you'll hopefully remember from Algebra 2 that with the unit circle, the cosine terms correspond to the x position of any point, and the sine terms correspond to the y positions of any point. Essentially saying that if we have cosine of an angle, that's going to be equal to this x value, or this x point. If we have sine of an angle, that's going to correspond to the y value of this point. So therefore, we know that cosine of this phi is equal to, let's say, our x, and that is equal to the cosine of the negative phi. So cosine negative phi is equal to cosine negative phi is equal to cosine phi. That's what we like to call an even function. Now with sine of negative phi is the negative value. Let's just say right here that sine of phi is equal to y. So sine of negative phi corresponds to this y point, which is our negative y. So sine of negative phi is equal to negative sine phi. And we like to call that an odd function. So that was a quick little aside, but let's get back to applying that for our problem. So let's plug that in here. So we're going to get that this is equal to c times parentheses cosine omega t times cosine of negative phi, which is the same as cosine of phi, minus sine omega t times sine of negative phi, which is negative sine phi. Negative sine phi. So here we have a minus, and then we're multiplying it by something that has another minus. So the two minus signs will cancel, so we can just write plus positive. And now let's distribute out the c for a second. So this is equal to c, I'm just going to rearrange the terms. Cosine phi times cosine omega t plus, distribute out the c here, c sine phi times sine of omega t. Now, I just want to point out that c and phi, they're both constants. It's not like they're functions of time. So since phi is a constant, cosine of phi and sine of phi just correspond to a constant value. So you can replace all the constant values, c cosine phi, was just another arbitrary constant name. Let's just call it a. And let's replace these constants. C sine phi was a constant with the same value. Let's call that b. So therefore, our original thing, we start off with c times cosine omega t minus phi. And now we found that that is equal to a cosine omega t plus b sine omega t. Well, we did it, and in doing so we showed that in this case we defined a as equal to c times cosine phi, and b is equal to c times sine phi. Okay, so let's just take a break right here. In the next video, we're going to find out what C and phi are in terms of A and B, and then we're just going to plug them back in here to really hammer in the fact that these two forms are related. So, I will see you in the next video.